Okay, so this morning I gave you a quick introduction to the uRiKA system and what it was. And so now I'll try to give you a little better example of the process by which you would actually use it to solve a real problem. It's a little bit different than simply writing your own C and C++ code to do your application directly. You're working with a new language, SPARQL, and a new data type, which is RDF. So, and then I'll also go through the processes by which you would actually get a big database problem solved. Okay, so I'll go through a quick overview of uRiKA, then how to convert data into RDF, data ingestion, how you do the querying, some visualization of the results. Okay, so basically the uRiKA system consists of three parts. There's the hardware engine, the Cray XMT2, which we've talked about a little bit. Typical systems are 2 terabytes, 32 terabytes for the uRiKA, and the multi-threaded processor. Okay, the new thing that we've added is an application that's written for the XMT2 that is a multi-threaded graph database. And this is known as an in-memory RDF quad store. I'll describe RDF in a moment, but basically it's a format for storing data that's the basis of semantic technology. The entire database is stored in memory, which leads to extremely rapid access and extremely rapid updates. And that's really the secret of the thing, is that when we're competing against other database products, our entire database is moved into the XMT's memory when you boot it up, and then it stays there, and it's updated in place. So there's the RDF quad store. We have a high-performance inference engine. I'll explain inferencing a little bit, but one of the big strengths of semantic technology is being able to make inferences about your data. You can actually define rules for relationships that need to be true across your database, and it will automatically execute those for you. And so when you're traversing the graph, you can basically put in rules, and it will follow them and find more data than was in the original database, because you have the database plus the rules. And then, of course, high-performance parallel I/O is very important, because you need to bring in these large databases, write out very large results, things like that. And then finally, the front end is, I mentioned it before, it's based on Jena. It's a complete semantic database that is the reference standard for the SPARQL language, and it's very widely used. There's an application framework that is grafted onto the front of that, so if you have applications, and I'll show one, that you can add, it's basically, the front end forms the basis of the infrastructure for your entire database system. Now, I don't know how many database people we have in the audience, but there's there's something called ETL, extract, transform, and load, and that is bringing data in from the outside world, transforming it into a form that's usable in your database, and then loading it. And so for every application, that's different, and I'll talk about that a little more. And then it's all SUSE Linux infrastructure, any language that you wish, any application you have. Jena is implemented in Java, for example. Okay, and the thing about it is it's basically a hybrid supercomputer running a semantic database. These service nodes, upon which a significant portion of the processing is done, are actually opterons running SUSE Linux and Jena. The thread-storm processors run MTK OS, which is the name of the OS for the XMT2, and they're completely pre-programmed. So to the outside world, it looks like the ordinary machine you're used to, except it runs really, really fast. It also uses supercomputer infrastructure, so it's a very reliable machine. It's a very high-speed interconnect. So basically trying to bring a supercomputer to the database world. Okay. The Web 3.0 standards are RDF and SPARQL. They've just emerged within the last decade or so, and they're just now gaining acceptance. Most important probably is RDF, Resource Description Format, and it's actually a very simple idea. Every atom in your database is recorded with only 3 quantities: subject, predicate, and object. And this is called a triple. In the case of our database, it's a quad because you add an additional field, but I'll talk about that in a second. But any of these can be what's called URIs, which are like URLs, Uniform Resource Locators, which is what you're used to seeing in your web browser. So it describes a location somewhere on the World Wide Web, except URI is a superset of that. It can also describe files and other things which are not exposed to the web. But basically, you can declare a logical relationship between 2 pieces of data anywhere on the planet. So in fact, you usually try to bring all the data that you want to work with rapidly into the XMT's memory for querying. But in fact, you can if you want to load databases from outside sites, you can simply refer to them there as a URI. This is useful for some of the very big bioinformatics databases, for example. OBO is pretty big and is maintained by someone else. This gobbledygook at the bottom is basically what RDF looks like in its natural form. And you can see they're all of the form subject, predicate, and object, where the predicate is describes the relationship between these 2 things. Subject and object usually represent some sort of, well, they're URIs, but they represent some sort of subject or idea. In this case, the name of some biological quantity. Any questions on RDF? Basically, once you've got any individual RDF atom or triple is very simple, but you combine a large number of them together in terms of nodes and edges. Any RDF triple basically consists of 2 nodes and 1 edge, and when you have a large number of nodes and edges, you have a graph. So this shows a very simple thing that shows relationship. Vancouver is in Canada. Canada is type country. Canada is on continent North America. Edmonton is in Canada, etc. So this data on this very, very small graph might be able to be put reasonably in a table, but there's a lot of data like phone records, for example, or Facebook communications that would be a ridiculously sparse graph. So you can think actually of RDF as being a sparse graph representation, but or relationships between proteins, for example. But it's a way of working with data that is not expressible in a tabular format. Okay. The second important standard is called SPARQL. Some of you may notice the similarity to the language SQL. SQL has been around for 30 or 40 years and is the language used to query relational databases. So they invented a new language called SPARQL. Let me see if I can remember what SPARQL. I can't remember what. It's a recursive acronym. It's like, what's that? That's right. I couldn't remember what. Yeah, SPARQL RDF query language. I'm sorry, I forgot what the R was. I should have. So, yeah. Anyway, it looks very similar to SQL, but it expresses things in terms of patterns, and basically. Matching graph patterns is its biggest strength. You define a graph pattern in your SPARQL query, and it goes out and searches your larger graph for other instances of it. So here's just this is some housekeeping. You define some prefixes to keep it small. This select statement says return 3 variables, x, y, and z, where this is this Lebum. This is taken from the Lehigh University benchmark. And so it says, find a student and a professor and a course where the student is taking a class from their faculty advisor. I'll have a picture of this later, but basically it's this represents a simple triangular pattern, and it will go out and find this in your database. Now this looks like a very simple sort of a pattern to find, but in fact this is very difficult for a traditional relational database. It was on this very query that we did so well against the Oracle Exadata, which is a very expensive machine, more expensive than an XMT actually. But the implied circle of 3 joins is very, very difficult for relational databases, but it's quite easy for a semantic database, especially a fast one. Okay, and just a reminder, this is our software stack. That query engine lives and the XMT live inside this box, and then the other layers on top. As I say, quite a few of your ETL apps will be here, and will simply run on the Linux machine and talk to Apache there. Okay. This is basically a functional view of the internals of uRiKA. So on the outside, you might have, this is a little representation of a SPARQL query. I'm not sure if you can read it. And then there'll be some sort of ingest application. This might be over HTTP. This might be a direct programmatic interface. But anyway, it's a way of bringing your outside queries into Jenna. Okay, once the query is come in, the SPARQL is converted to a lower level form called SPARQL algebra. It's basically a parsed, machine-readable version. It's an intermediate representation that goes to this API. Now, one of the problems with the machine, or strengths perhaps, is that we have 2 different operating systems on either side of this API. You have your SUSE Linux and your MTK. So you have to be able to work back and forth across this API. This does thankfully happen on the high-speed network, but you send that over. It's parsed and interpreted and sent to the query engine. The database, actually represented here, consists of quads. Usually RDF is referred to as RDF triples, but in fact in the standard they add one additional field called graph. And it allows additional flexibility so that basically you can have subgroups of triples. So the triples are the basic data items, but you can group them into sets by having this additional graph field. And it's incorporated into your SPARQL queries. It's kind of a minor point, really. But the internal structure of the database, believe it or not, is 4 tall columns. So it's relatively simple. But the SPARQL engine contains some very sophisticated indexing that works very, very well to be able to access any portion of this very rapidly. The thing is we've talked about this. It's not a column store. Because of the nature of the XMT already distributes this very evenly around the memory bank in a way that balances network bandwidth and thread use. So even though this appears logically as 4 simple columns, the hardware of the XMT generates a very, very sophisticated memory allocation. I'm pleased to say that I actually wrote the query engine for this. I wrote the first one, and now we've got a much bigger team of people working on it. So they don't let me work on it anymore, but say proud to architect the first one. Okay, that's fine. Yeah. So now what I'd like to try to explain is what sort of workflow you would use when someone asked me a question earlier. When someone comes to me with a problem that they'd like to run on uRiKA, what do I need to do? What's the workflow? So step one is take whatever data you have and convert it to RDF. Everything in the store must be in an RDF format. And sometimes a customer will come to you with data that's already in RDF format, in which case that's great. But otherwise, they may need to go through various ETL programs to be able to convert this into an RDF store, into something suitable to be loaded into an RDF store. Once it's converted, you just simply do an ingest step. You query using the SPARQL language. Visualize the results. I'll show a simple visualizer, but there are quite a few out there that are very good. So you try to understand your results, and then mostly you iterate back and forth between querying and visualizing. But then you might go back to the beginning, and you might generate new data. You can generate data using the database and reload it back in, or else you might select new data that you might want to use. So I'll be covering this workflow. Any questions on? Yes? Yeah. Oh, yes. The subject can be almost anything of any size or length. The URIs are a description of some object which can be either local or remote. And when the graph is ingested into when the URIs are ingested into the database, they're all converted to references that are single 64-bit integers. And so, and this is transparent to the user, but the URI can be almost anything. Now you asked, is it a picture? It could be a picture.
If we have a satellite data, and this is just a picture normally.
Oh, okay, yeah.
And if I have the satellite data, it generates like statements, and then it describes each of those pictures in some this RDF format, for example, and then store it, and then search through those pictures somehow, or connect them to each other.
Yes, and that actually is a very common usage of this sort of thing, is that you're not making logical associations about the picture itself, but about perhaps metadata associated with it. Like this has been used to create a medical image library. So you have a large number of images that might be I think it was X-rays in this case, or CAT scans, something like that. And each one has quite a bit of metadata associated with it, you know, patient, disease, etc. And so you could put in a query like, show me all the patients between ages of this and that who had this sort of problem, etc. So, or for example, I guess in your thing with satellite data, we're working with NASA on a project to query that. In the climate knowledge discovery field, we also looked at storing and manipulating metadata that was associated with various pictures. And this is a very important thing to do. The uRiKA will not do any image processing itself. It cannot make any logical inferences about the picture unless you, when you convert the data to RDF, you might, like I say in the case of the medical images, you have an image and someone, either an automated program or a doctor or something like that, says this person has little spots all over their lungs and lightning in their, thoracic veins or something like that. So there would be some information that you would store about that picture, and that would be metadata associated with the picture. So you would have one URI that represented the picture itself, which might be its location in the store, and then you would associate all sorts of other data, patient's age or satellite that it came from, et cetera. And then you'd be able to logically reason across that metadata. However, someone else has to convert to RDF. The same is true of documents, for example. If you have an article in Medline is a paper that talks about how two genes interact. You'd have to convert that into an RDF format using natural language processing or something like that. And then you'd say, there's this document, and you extract the logical inferences from the document. You associate them with the document, creating a little subgraph that is associated with only that document, and then you reason across that. And I'm glad you asked that, because that's actually probably one of the most important aspects of using a semantic database is the data modeling process. You have to decide what's important about your objects, and you treat them as little atoms, little nodes in the graph. But the URI associated with that picture is exactly the location of that thing in the graph. So if you have a logical specification for what you'd like to find, it will return you the file locations of all the pictures that you wanted. And I'll go into that a little more. Yes?
If my data is not
Uh-huh.
I want to compare the stock with stock location for the last year. So that means that I have 300 more or less values for each stock.
Mm-hmm.
For example, I want to see, for example, two stocks are for the day.
Mm-hmm.
To convert my numerical vectors into
Mm-hmm.
something that can be submitted to uRiKA,
Right.
I think I have to subdivide my numerical value in intervals.
Let me see. Yes, and
How can I
work with them.
build a LDF, let's say, stock A has value 34.
Right. You can for either the subject or actually for the object, you can use what's called a literal value, like the current value of Facebook stock might be $41 or something like that. And there's a SPARQL function called filter that is very, very complex that will let you do. You can say, is this literal greater than that literal? You can do arithmetic operations on them. If you asked me to, show if you had stock prices by day, show me all of the days where the stock price was over 42.375. So all relationships in a SPARQL database are logical relationships, but you can have numeric literals, and you can do manipulations of the numeric literals. So, and as a matter of fact, figuring out how the stock market works is one of our big applications. Basically, watching stock prices and comparing them to other things that are going on. I mean, the stock prices by themselves are not interesting, but if you can compare them with newspaper articles or other bits of information, as long as they're all expressed in an RDF format, you can bring them in and reason them. It's like another one is what's the name of that? Insider trading fraud. Find all the other stocks that raised right before this one did. Find the people that if you look for a pattern of bad behavior in the stock market, you can express it as a pattern and then look for it in all the data. Okay. And as I mentioned, here's our implementation. Extract and convert, we have a couple of programs now. D2R I'll talk about. And then the ingest and query is done by the query engine. Jenna on the front end and the Cray query engine, CQE on the back. And then finally, for visualization, we have a number of different ways, RelFinder, Snorkel, and we're adding more all the time. Cytoscape is another widely used program. So that's basically this just describes the process. Okay, so getting data into RDF format, I've already been addressing. If you're lucky and someone has RDF, it goes straight in. We have a program called D2R that basically is designed for converting data from in SQL database format into RDF format. And of course you say, why is that useful? If you have many, many different SQL databases with different background schemas, you really do need a RDF store to make sense of them. You can use data from Accumulo, another application, Hadoop, and then you need to build your own converter to RDF. And we have some of these under construction, and mostly everyone has their own favorite converter program. So we're trying to see how many of those we can support. And we've actually written recently an HDF4 converter. So it's expressing, if that's what you meant by pictures, if you meant HDF4 files. Ah, okay, yeah. Yeah, this was under a request from NASA to do some analysis on satellite data. And in that case, you need to this is a case of taking individual points within that HDF4 file and associating them with numeric literals. You know, the temperature here or the radiance value there. Yeah.
So question, how can you code the metadata in HDF4? For example, or how can you create RDF out of HDF4? Because, well, what you can do is basically either subjects or objects, yeah?
Mm-hmm.
So predicates are missing it. So somebody should provide that as well, isn't it?
Yes, and that is absolutely part of the data modeling process, is you have to define how you want to convert that. So,
okay, so that's not the raw HDF format, but some like basic that should be annotated.
right, what you do is you describe, I wasn't prepared to talk about that, but you have to describe an ontology that describes the relationship between all of these different things. And
I remember from the last year we can encounter that for the very first patient. How cannot be RDF, what is RDF, everything that you created, that you already recognize?
right, well, the answer is it's a lot of work. The data modeling and ontology building and stuff and converting everything, you can do a lot once you have it in RDF format. You can draw any logical inference you want, but much of the data in the real world isn't in RDF format. So I don't mean to downplay the challenge, and this getting data into RDF format is probably the biggest challenge of the whole semantic world. Right now, we only support 2 native formats, N triples and N quads. We're adding more formats in the future. Okay, so actually, you actually knew what was happening on the next slide, but you want to be able to fuse data from different sources and model data. So ontologies are necessary, and those are definitions of entities and relationships. And so when you, I guess to use the NASA example, imagine you have one file that is radiance data taken by an instrument on a satellite that measures brightness on the ground immediately below you, and you'd like to figure out what causes that brightness to go up and down. Well, you might have some other data files which have cloud cover data, and so what you need to say is, in order to correlate your radiance data to your cloud cover data, you have to have some sort of rules for what cloud cover might be called in the other format, or how they're related to each other. Some sort of logical relationship, like where they might be located or what they might do. So you have to for all of the data, in order to be able to interact across different data sets, you have to have some sort of mapping. Think of ontology as just being a mapping. It can be as simple as a thesaurus, since many proteins have the same name, for example, or same protein has many names, or else it could be very complex. It could be logical relationships. So ontology mapping is a big part of the data conversion process. There are existing open source and commercial ontology tools. Here's our favorite top-grade composer, but there are many others out there. And so everyone has their favorite, and we're always adding new ones. But ontology mapping is a big part of your data modeling too. That typically, ontology building and mapping usually has to be done by a subject matter expert, someone who's an expert in the field. So if someone knows a lot about satellites, they have to write the ontologies. I won't know. I haven't a clue. So.
Yeah, that's also a great challenge for the CSCS. Sometimes it can be good.
Oh, yeah.
It would be great for a live because I think that it seems usually slow.
Oh, no, it certainly will. So, and we're working with them to try to do that. And then, of course, once you have one RDF format, you can convert across it through some of these other tools. RDF to RDF is the one we use most often. Riot, just part of the input and conversion process. Okay. Like it or not, most data exists in SQL databases. And so we use this program called D2R, that's a mapping generator. It's fairly straightforward to do. You just say generate mapping, and it will do its best. Sometimes, of course, the SQL database might be very subtle, or there might be relationships in there. So you sometimes have to edit the map a little bit. But it's basically fairly automatic. The SQL databases tend to be much simpler than a graph database. So the tables have very straightforward relationships. But it's important to see that you get the right mapping to answer the questions that you want. And then you move it onto the file system. Okay. I mentioned that one of the big advantages of this is moving in external data. So if you're importing data from some Accumulo is a data ETL tool that is widely used in intelligence community. You have some external data store and send out an external request. It waits for data to be generated using triggers. It returns the data in n triples or n quads. Accumulo has that export. Your Hadoop application would have to have it written into it. And then you can transfer and load. So this can be fairly automatic. So you can work with other stores to bring data into the uRiKA to do semantic graph analysis. And this is a very important part of our story, to be able to work with either SQL or Accumulo or Hadoop, anything like that, to analyze data. Okay. Once it's actually, the difficult part is really converting data into RDF. After it's been converted to RDF, all you do is move all of the files containing the data onto the Lustre file system. Now, Lustre is our high-speed parallel file system, but I know that here at CSCS you use a different high-speed parallel file system that is GPFS and Lustre. You use both? Oh, okay. I had thought that this particular machine was associated with a GPFS file system. Oh, anyway. Okay. You can talk to either. Anyway, any sort of data ingest process has to be extremely rapid. So all of this has to happen from your parallel file system, whichever it happens to be. So you bring it in. There are your data files, all the data files that you've generated from RDF. And then you bring in something called a rules file, which performs all of the inferencing that you asked for. We have a very high-speed parallel inference program. We believe is the fastest in the industry. And so what it does is it takes the data that you have, it applies all of the rules to it, and then it creates additional triples that instantiate those rules. And this is for performance. That way we do not have to do the inferencing at runtime or at query time. It's a trade-off of basically memory for performance. And so we chose to instantiate additional triples, add them to the database, and it makes for a much higher performance query engine. So basically, once you put your files in Lustre, hit load, and it's loaded onto the machine. Yeah. Yes, you're quite right that if your nest of inferences are too deep, you can create a bigger output file than your machine can store. But it will try various times, and then finally it will come back with an error message that your inferencing was too deep. The inferencing program is run separately from the query engine, so you won't get a runtime crash from inferencing. What you'll do is your logical rules will simply create a database that is too big for the machine to run, and you'll already know that. It's blocked, so you can certainly create and store on disk a database that is far, far larger than the memory of your machine. So you could use a small machine to create a database for a big one, but that's just a... Yes, to be actuated upon, all data is always loaded in memory. I have a slide on that. Our current version does not support updates, but our next version, due out in September, will support updates. Yes, it will. Yeah, that's... well, no, I mean, I know it will happen, but yeah, I mean, if you running very complex inferencing rules can lead to a great expansion in the number of triples. In Lubum, it's about 30%, but other things it can be 3x or 4x. Right. So, I mean, if you load in too much, if you're doing an update and you load in too much data, then you've overflowed. It's just like anything else. I mean, it will retry for a long time, but then it will finally give up and tell you that it can't do it. But yeah.
Question, do you know whether in Jena during updating the database, do you need to stop for the query process or change around later?
Oh, you need to stop it, and that's part of the SPARQL 1.1 update specification. And it's to make sure that you have data consistency, or at least that's why I think they put it in the spec, is that when you put an update request in, it stops querying, performs the update, and then lets the query queue open again. And that's the way it's defined, and we're glad that that's the way it's defined because, in fact, that's simpler to implement. Otherwise, you have, I mean, we have our full empty bits, so we could work around that, but it brings up a bunch of other interesting questions. Yes, another question? Right. You can either introduce a time variable. You can add it. You can basically, and this is very important for stocks, for example. You need to know like what's the stock price today and what's the stock price tomorrow. So you can what they call reify is basically hang some extra data off each one associated with the date. And say, had price at this date, had price at that date, etc. You can use the graph field to create additional graphs. Handling things that change in time is an interesting modeling question. We have enough hardware and software to support it, but how you actually do things that change in time is up to the modeler, really. So, I mean, one thing you can do is if you want to have only one copy of a variable, we have update and we have insert and delete, which are two different things. So you can first delete the old stock price and then insert the new stock price. if you wished to do that. Right. Okay. Yeah. Well, it's a complex issue, and maybe we can talk about it tomorrow. But basically, it's you just delete the triple that says Alaska part of USA, and then insert the triple Alaska part of Russia. Uh-huh. Okay, yeah. How you model time, as I say, is a great debate. There's no SPARQL standard for it yet either, let's say.
In terms of this question, there are special reasons to allow users. Basically, actually, even the starting class, we can match your buttons related to this language, for example, then we can find examples related to the query. And then also we can use SPARQL query to make it is possible everything using these SPARQL queries.
Yeah, you can do it yourself using the existing SPARQL specification, and there is a draft standard for a standard way of handling time varying calamities in SPARQL. Right, and how you do time is different if it's millisecond or like events, how many times you've got. If it's years, then 10 graphs might be enough for you. But if it's milliseconds, then you have to do something else. Okay. Now I was talking about data ingestion. Basically, we have a user interface that allows the user to go through to control the loading process. And this is basically the UI that we've built for the uRiKA appliance. Right now, it's relatively unsophisticated, but we're putting together a complete DBA administrator package. This is what we have now. So that's kind of hard to read, but there's an import data slide where that is hard to read. I'm going to have to change these slides. Basically, you give it the file that you will need. Go to a different tab and tell it what inferencing rules you wish to use for that particular database. Do a database build. And what a database build means is to take all of your different files and convert them into that internal representation that I mentioned, because that's actually done both for querying speed and for compression. These URIs can be hundreds and hundreds of characters, and often are. But we convert every single one of them into a 64-bit integer. So often the database is far larger than the memory of the machine until it's converted into this internal representation. And the build process also performs the static inferencing that I mentioned earlier. So quite a bit happens, but we put a lot of work into parallelizing this step, so it happens pretty quickly. And then load basically is you use once it's built, use the parallel file system to load it, and that's it. And we have a help screen to help you do it. So under the covers, it's complex, but in terms of operation, it's quite simple. That's the idea behind the whole thing. Okay. Now querying. Here's the way that I always tend to think of these SPARQL queries. I mean, here's the same query that we looked at before, which is show me all students who are taking a course from their faculty advisor. I think it's a lot easier to look at here. This node X is type student. This node Z is type course. Y is type faculty. And we have this triangular relationship between them. Professor is teacher of course. Student has advisor, professor, and then student takes course. So basically, when you have three variables here, x, y, and z, which are the what the query is asking for. Give me all sets of these three variables that satisfy this pattern. And so when you see one show up in multiple locations, that basically requires a join between, you see it as a join here on the screen, and it's similar sort of to what a relational database would call a join, except that all of these joins are implicit and are performed by the database engine itself as part of its processing. In a SQL database, you actually have to explicitly call out what you want to join to what and where. And if the database gets very complex, defining all of these joins is why it takes weeks and weeks to write a SQL query. So the fact that these are implicit, you just place a variable in two places and it will just go off into the database and find all relationships for which that's true, is actually probably the biggest strength of this approach, is the fact that these joins are implicit. What's that? Yes, that's it. Right, and they have their own very complex schemas and things. And the way that most relational databases work is you have DBAs that understand how everything is laid out and where everything is hidden. And you take a question, you go to the DBAs, and they come back 2 weeks later with a query, and then you use that query many, 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 many times. And so that's one model, and if it's airline reservations, that's a good model, and that's why there's so many. But if you want to find relationships between proteins or something like that, you might try one pattern, and then try another, and then try another, and then try another. And if each time it took 2 weeks to get the query written, then it's difficult. And the reason that it's so much easier in SPARQL rather than SQL is that you do not have to understand how the data is laid out. It's just a big graph. And you define a pattern, which is the pattern you're looking for, and then it goes and finds it. And that's the job of the query engine. So I know that's, it's basically you have to write a, I've never written these giant SPARQL SQL queries, but everyone tells me that.
Certainly not the issue of writing, but the issue of evaluation. The data can be noisy, even, and so on.
Mm-hmm.
That's why to roll the result and CMT, nothing to be
mm-hmm. Oh, okay, yeah, okay. Here's our roadmap for implementing the SPARQL for the SPARQL language. The current uRiKA release, which is what's running now on the machine, covers SPARQL 1.0. So you can see that the SPARQL language is very recent. The first 1.0 is 2008. It has a read-only database. So once the database exists, there's no such thing as an update. That was just the first version. And it covers basic pattern matching, filters, unions, a bunch of other things. So you can do a lot of things with SPARQL 1.0. The next release will cover SPARQL 1.1, which was released in November of this last year. So this is all hot off the presses. We have all of SPARQL 1.1 implemented except for property paths, and that's because they generated this specification called property paths, sent it out there, and someone pointed out that it could result in yottabytes of data from a very, very simple query. It asked for all the paths you can define for a certain thing. So they had to bring one section of the spec back, but we'll have the whole thing as soon as it's ready. Improved DBA interface, more complex than what I showed, and then more input file formats. And then finally, very important thing is SPARQL updates. So we'll have high-speed in-memory updates to the database, which is one of the most requested features, high-speed updates, because of the dynamic nature of a lot of this data. Any questions on the SPARQL? Yeah.
When you just support SPARQL is an emerging standard.
Mm-hmm.
Well, that's basically when the RDF data is
Oh.
especially for simulation. like in the smart cities domain, people coming from the sensors and are only relatively some amount of time.
Okay. SPARQL? I've not heard of it actually. I'll
Just basically training more relatively.
yeah, I'm not aware that we're looking.
Specify the time frame for the data that you
Okay, I know that there is an emerging standard for how to handle time in SPARQL. I don't know if it's called SPARQL or not. Probably not. Okay, say it's a work in progress. SPARQL in general, there are a lot of.
It's based in SPARQL 1.1.
Based on 1.1. Okay. Yeah, we're not there with 1.1, or we won't be there until September. We're working on it furiously even as we speak. There's another question? Uh-huh. Mm-hmm. Yes, it is absolutely a subgraph isomorphism problem. No, no, there are no false positives, and if it's in the graph, we will find it. So it's not. There are some partial implementations, and
But there might be patterns in the graph that
there are right. There are patterns that are very difficult for us to catch because they generate a large number of intermediate results. People have been able to come up with pathological queries that generate too many intermediate patterns for us to actually solve. So it's possible to write something. I'd like to say it's a good design, but yeah. Yes, and that is, if you ask for an extremely large random or extremely large click, that is one of the ones that can, that can generate too many. And as a matter of fact, that was the problem with the property path specification, is that it was not well enough defined that you could get an explosion of intermediate results, a very steep explosion. But yes, n clicks above a certain size are just difficult. It will try, but you'll run out of memory, unfortunately. Yeah, and I guess the only saving grace is that people, practical queries don't ask for n clicks very often. That's all I can say. Yeah. Mm-hmm. Yes, that's quite right. The uRiKA appliance is an RDF database, and that's its primary function. So the Cray XMT has many good graph algorithms that are. It's very good at a wide variety of graph algorithms. The SPARQL language only expresses a certain subset of all of that functionality. One of the most common questions I get is, once I've got this loaded in RDF, can I do betweenest centrality on it? Can I do shortest path? And that's not defined in the SPARQL spec, and we do not have it implemented. So the answer for today is no. You would have to actually write your own program in C++ and run it separately on the same XMT. But you couldn't run it on the uRiKA appliance. Now that said, there are efforts underway to put in an API, a programming interface, that will allow people to connect libraries to this graph store. Basically, the graph store that we have with its indices looks very much like a sparse matrix representation of the graph. You can interpret it as a fairly standard sparse matrix representation. We need to put together an API and then connect things like MTGL and other graph analytic tools to that. This is when we first designed this, we thought that people would be happy with the simple Spark. We're basically trying to follow the SPARQL specification as closely as we can. However, many people say, well, now that this is all very well, but I'd like to run between the centrality on that. So we've got a program to attach an API to the data store and allow other graph requests that are not part of SPARQL standard. Yeah. Well, we haven't. Well, the short answer is that the XMT is very good at indirect addressing. So the choice of format, I don't know. John, sounds like you had an opinion on that? Yeah, we believe it would be simple to add that, but it's under development at this point. Say we're until September anyway, we'd be working very hard just to complete the entire SPARQL 1.1 spec. So we'll do that first. That's the minimum required to supply the latest database requirements, and then of course everyone asks for that. So it's a good question. Okay. Inferencing I've already mentioned. Here's an example of what the rules look like. So in your schema, you might define a rule like sports car is a subclass of car. So you say, these are basically rules that define your data set. So you say, vehicle is a class, car is a subclass of vehicle, and then sports car is a subclass of car. So then if you say that you have somewhere in your data you have a little thing that says Ferrari Enzo is a sports car. And then you have a query which is select a variable called car where car is in fact a member of the set of cars. So if inferencing is turned off or you do not include this rule, then your query will return these two things that are defined as car. With inferencing turned on, it will make the additional logical relationship that sports car is a subclass of car. So this is a very, very simple rule, but you can see how you can actually find things in your data which weren't originally there. You can find out that Ferrari is in fact a car, even though that triple does not appear in your database. Does not appear in the data that you read into it. Inferencing will create the new triple. Ferrari Enzo is a car. So in this case, you would have one additional triple added into your database. But it's a very, most databases are expressed in terms of the underlying data plus rules relating them. And we have a very high performance parallel inferencer that we're very proud of. So, you had a question? It is similar. Yeah. I think it's not the same. There's the inferencing. This is a simple querying rule, but I think that inferencing in general, there are many different rule sets, and some of them are more complex than transitive closure. Some of them are equivalent. Some of them are more complex. It's I guess the best I can answer. Yes, it's when you load your data, as on that earlier slide, you added another ASCII file called rules.txt, and for this example, it would consist of a single line. Sports car is a subclass of car, and then when you loaded your database, all that inferencing would be performed, and all of the results would be stored in the database, and then you could make the correct query here. So it's in the same format as all the rest of our input files. There's a certain ASCII file called turtle, or ASCII format called turtle, and it's human readable. Let's say this is exactly what it would look like if you opened it in VI. Okay. Any other questions on inferencing? I mean, inferencing is one of the major fields of research in semantic technology. Yes?
So when you do this inferencing, so if I take another vendor solution, like yours, and I will perform the same query on the system, I will have different answers because you are doing inferencing and the other vendor is not doing inferencing. So if I buy Oracle stuff and I put the same database, I got answers that are not the same to the first answer. I run into those systems.
Right. There are standards for inferencing rules, and you have to implement the standards. So our database, or uRiKA, supports something called RDFS, which is one of the inferencing standards. There are more complex ones called OWL and OWLDL and things like that. So as long as the two databases are supporting the same inferencing standard, and you put in the same rules, it should always give you the same answer. If it's implemented correctly. So yeah.
Just to clarify, there are two types of inferencing. These are forward chaining, closure, and vector, right?
Yes.
So forward chaining is based on the pre-processing step, which is in graph closure interpretation, where all the answers are recomputed and then variant of returns over the recomputed answer. Where the vector chain reasoning goes in the other way around, and just compute some reply of the answers to the given query. So I get this is the second one, right? Isn't it?
This is all forward inferencing. Our current parallel inferencer supports forward inferencing on the RDFS rule set. So we do not have backward inferencing at this time.
Do you compute the closure interpretation, or how do you materialize it?
It's a static materialization at database load time.
Okay.
Yeah. And actually we had and I applied with a bunch of other folks, including SciCorp, to do a grant to study dynamic inferencing in this format. But it's a very complex thing, and we didn't get the grant. So we would like to eventually have dynamic inferencing and backward inferencing. So we're going to keep, basically, forward inferencing with a static materialization is what we can do now with good performance. We would like to do dynamic inferencing for various reasons, and backward reasoning would be nice too. So one of the things about the different standards for inferencing is they go from very simple to very, very complex. I mean, full OWL reasoning has not been implemented by anyone that I'm aware of. So you just have to be careful that the inferencing that you've chosen matches your data.
One more question.
Yeah.
The performance results in the showing before, they refer to clearing the pre-computed type, So I mean, the pre-computed closure or that code would be closure computation. So where the query response time.
Oh, the query response time is absolutely on the inferenced graph, if that's what you mean. We could turn inferencing off, and the performance would be about the same. That's the reason that we like the static inferencing, is that it results in almost no loss of. In general, it doesn't result in a loss of speed, since the querying speed is not that dependent upon the database size. It makes it bigger.
Okay, you can put the closure time of the first in it, or do you do it like once or something?
Oh, the time we quoted was the time to actually perform the inferencing. It's hard to benchmark against something that's static inference and something that's dynamically inferenced. I mean, Oracle, however, used a static. Oracle used an identical static materialization as we did in the benchmark. So those benchmark numbers are indeed apple to apple. We'll have to take that one offline. It's a very complex.
Because I guess in the end, it's like by every new triple able to change the database, the closure must not be serialized.
Yes.
I'm not sure how this applies.
When you do add new triples to the database, new inferencing must be performed on those triples, is the quick answer to it. But we have that figured out. Okay. So visualizing results, this is mostly under construction. We have a single package called RelFinder that you can use to explore data. It's not very full-featured. There are some other ones called SiteEscape, a couple of others that we're looking at bringing in. And then we have an interface defined so that you can attach your favorite visualization tool to it. But visualization packages are still very much under construction, and there isn't really an industry standard yet. Mostly it's application dependent. This shows RelFinder, and I'm afraid that the light gray does not turn out very well in this room. You have basically various, you can show on the screen various nodes and edges that you have, and it will show the relationships between them and highlight them, things like that. But in this case, it shows the Ferrari and the, I think they were using race cars again. I'm sorry, this didn't show up very well. So basically, in summary, the uRiKA appliance is targeted at large-scale semantic graph processing. That relates to your earlier question. That's what it's for. It's an RDF SPARQL semantic graph database. Some flows need more extract ETL components, and we're basically working with a bunch of different vendors and looking at open source packages to qualify the best ones. We have decided not to try to qualify everything, since everyone has a different favorite, and so we're finding out what people like and trying to support the best. So that's all.